So one of the last sections in Chapter 3 discusses uniform circular motion. We've sort of talked a little bit about circular motion in a disguised sort of manner, but we're going to put a little bit more emphasis on it today and slap an equation or two on it as well. Right, but just to sort of summarize where we're at so far. All right, so far we have objects moving in 1D. Easy stuff. All right, objects moving in straight lines back and forth. Obviously, if you're moving in 1D, you're not capable of making a circle because a circle is inherently 2D. We have sort of a special case. We spent some time on a special case of 2D motion. In particular, we've sort of focused on problems where you can break a single 1D problem up into a single 2D problem up into two 1D problems, right? That was sort of my focus. So what that meant is that motion in one direction was independent of motion in the other direction. Now if you remember when I first mentioned that phrase, I said most of the time 2D problems can be treated this way, but that's not always the case. So circular motion is an example of when that's not really the case because the motion in one direction does depend on motion in the other direction. Now, in particular, we've really focused on problems with a constant acceleration. That's not to say all of your problems have been under the assumption of constant acceleration. In fact, that's one of the issues I've seen on some of your homework sheets is that there were a couple problems where they were not constant acceleration, but you tried to use the kinematic equations to solve them anyway, because why not? So we've done a couple of problems where you were given an equation for acceleration that wasn't constant. But uniform circular motion is, by definition, a non-constant acceleration problem. Okay, and we've sort of talked about that like a week and a half ago, and we'll come back to that now. Okay, so what does that mean? Uniform circular motion, which I will abbreviate UCM, non-constant acceleration. So it's more interesting, maybe. Okay, but what exactly is uniform circular motion? Okay, it's motion with a non-constant acceleration, but there is something unique about the velocity. All right? Yeah, the acceleration isn't constant, but the speed is constant. So it's motion at a constant speed with a non-constant acceleration. So let me draw a picture. Go away. Uniform circular motion is motion in a circle. I know, it's surprising. Very difficult for me to draw circles. It's not bad. Okay, so what we have is we have an object going in a circle. And if I label a few points of interest here, I'll just pick them sort of at random. I can draw velocity vectors at each of these 2 points. So tell me about, let's give them letters because letters are fun. So tell me about the tell me about the velocity at point A here. Just the direction. Straight up. Good. All right, so at point A, I guess it could be straight down, but we'll make the thing go clockwise. All right, good, straight up. So what about the velocity at point B? That seems right in my strange perspective. Good. So we're drawing it's sort of on a diagonal here. At point C, straight out to the right. In other words, I'm drawing vectors that are what to the circle? Tangent to the circle. So my velocity vector, when I'm undergoing uniform circular motion, my velocity vector is always tangent to the circle. In fact, that's always true. All right? Your velocity vector is always tangent to your trajectory. Okay, whatever your trajectory happens to be. All right. Let's take a look here. I want to break this up sort of in really sort of obvious terms. So I'm going to do a little bit of a chart, not a chart, a table. And we're going to look at just 4 of those points. And we're going to write down a few different numbers that describe the motion at those points. We're going to write down the speed or the magnitude of the velocity. We're going to write down each component of the velocity, so Vx and Vy. Actually, Vx, and we're going to call it something like delta Vx, so the change in the x velocity. We'll write down Vy and then delta Vy. Okay, so delta Vx and delta Vy is the change in velocity from one point to the next point. All right, so I said this thing is in uniform circular motion, which means that the speed is constant. So we'll just give the speed something like 30. I'm going to leave units off here. Everything is in SI, so 30 meters per second. Okay? So then the question is, all right, well, how does the speed, so the speed, the x component of the speed at point A, that's what? 0. The x component of the velocity, I'm sorry, I should say. It's 0 because the velocity vector is straight up. And of course, you're assuming that I'm using our standard horizontal and vertical x and y coordinate system. Good. How about at point B? Is it 0 there? No, it's not 0. It's somewhere in between. It depends on what the angle is or something like that. But it's somewhere in between 0 and 30. All right, so I'm just going to go ahead and write down 21, because why not? Point C, what's the x component of the velocity? 30. Good. All right, all of my motion is in the horizontal direction, so it's 30. And then at point D, again, we're sort of in between. We'll use 21. Okay, so that means that allows me to write down a delta Vx. So I just take the velocity at the next point forward and subtract the point that you're at. So this would be something like plus 21 plus 9 minus 9, all in meters per second. Okay? Are you raising your hand? You're half raising your hand? No. I'm sure. Okay, fair enough. All right, cool. So let's do the same thing in the y direction. At point A, all of my motion is in the y direction, so we're cruising along at 30 meters per second in the y direction. At point B, we're somewhere in between, so we'll say 21. At point C, all of my motion is in the x direction, so we'll say 0. And then at point D, my motion now is starting to curve back around to the negative y direction, so we're probably moving at like negative 21 meters per second. All right. Same sort of thing as before. The delta Vy now looks like minus 9, looks like minus 21, looks like minus 21. So if you're sort of thinking ahead, where am I going with this? Well, if you look at this chart, you can clearly see that both the acceleration in the x direction and ay are changing. Why? Because the acceleration is simply the change in the velocity divided by time. These points are sort of equally spaced, so we sort of think of them equally spaced in time. So delta t is always the same, but if delta x or delta y is changing from point to point, that means our acceleration must be changing. All right, so we certainly have a non-constant acceleration. Okay, but as it turns out, the magnitude of the acceleration isn't changing. And that's sort of important. That's why we like uniform circular motion, because the magnitude doesn't actually change. And we're going to take just a few minutes to look at, why that is. But really what I'm saying is A is proportional, we know this already, to something like the change in, that's not an n, and Vx squared plus the change in Vy squared. So the question is, if you add those two things together, the change in Vx squared, that's not a Vx, sorry, not Vz, Vx. The change in Vx squared, if you add these two things together, change in Vx squared plus the change in Vy squared, take the square root, is that constant? And for uniform circular motion, I can tell you it is. All right, let's take a look at this really quick though. All right, so what we're really saying here is, I really wish that wouldn't happen. What we're really saying here is though, in summary, for uniform circular motion, magnitude of the velocity always stays the same. Okay, but the direction changes. I like to say things over and over and over again so they get stuck in your head. And then we'll do things over and over and over again. All right, so how could I describe motion? Let's draw another picture here. All right, so we have an x and y coordinate system, and we're going to be moving in a circle. Not bad. And I can label a few things here. Let's pretend that I'm at some point on the circle right here. And we're moving. The velocity vector, therefore, is like so, tangent to the circle. So this is v vector. I can label this circle has some radius. So I'm going to label it as capital R. And the position vector is subtended by some angle theta. Okay, this picture should sort of look similar to some people because it's sort of like a unit circle type thing. A little bit later, I'm going to be at this position right here, moving with some velocity vector v. Okay, again, the magnitude of v is the same. And the amount of time that it takes me to get from this point up here, we'll call it point A to point B, is t, the amount of time t. All right? So if I write down my position as a function of time, what might that look like? What say you, people?
Would it be fair to start off with v times time?
V times time. Okay, but we need to know v is a function of time then. Remember, v is a vector. All right, not a bad idea. Just think about trig here. You know, a little bit of geometry on the circle. How does x change as a function of time? All right, what do you think it depends on as far as things that I've labeled here? What's that? All right, certainly depends on the angle. If it depends on the angle, it's got to have there's got to be a trig function associated with it, right? All right, so how does it depend on the angle then? Tangent, sine, or cosine? So remember, we're talking about my x position, which is the projection down from this point onto the x-axis. It's cosine. All right, because the x projection is the length of some side from here to the projection right here. So that's my x. All right, good. So cosine theta is certainly important. What goes in front of cosine theta? R, good. All right, so our position of function of time is r times cosine theta. Fair enough. I could also write down an expression for my velocity as a function of theta and r. We're going to see this a lot in a little bit. In, I don't know, a few chapters, we're going to come back and study angular motion more. So you'll see something like this again. But for now, I'm just going to write down v is a function of theta and r. It's equal to theta divided by t or theta divided by t times r. So what this looks like is, you know, what is my angular rate of change? Kind of. Times the radius. Okay, so this thing, theta divided by t, is actually called the angular speed, which we'll come back to in a little while. We multiply that by the radius, we get the actual normal velocity that we're comfortable with dealing with, right? So this is the magnitude of the velocity. So I've got a couple of things I can work with here, and then what I'm going to actually do is I'm going to make use of our definition for theta that involves v. So I'm going to rearrange. I'm going to bring theta over to the left-hand side and solve for it. All right. So really, then what we have is theta is equal to v times t divided by r. All right, so what that allows me to do then is write down my position as a function of time using that stuff. So what we have is r times cosine of theta, which is actually v times t over r, which is nice because we know that v is a constant. All right, our speed is a constant. We like that. All right, I can write down a similar equation for my y position, of course. Like so. All right, so I've got my x and y position. Now I could also go ahead and take the next step, and now I can come back and write down a velocity as a function of time. Right? Notice again, this is speed, so that's constant, but my x and y components of my velocity are not constant. Right? That's just the derivative of x with respect to time. So I always have to remember, drink Coke, not Sprite. Derivative of cosine is negative sine, so we're going to get a negative r times v divided by r times sine of vt over r. All right, so the r's cancel, and so our velocity in the x direction is just the speed times the sine of the speed times t over r. Similarly, for the y direction, I get minus v times cosine. Sorry, not minus. Just v times cosine of vt over r. You guys all learn drink Coke, not Sprite? No? I study no calculus. The integral of sine is negative. No. Which mnemonics did you guys have? What? Oh, no mnemonic? Fair enough. So it's funny, the things when you take calculus that you think just everybody learns. Apparently not. It's very important stuff. Okay, and finally we could go one more step and solve for the acceleration and the x and the y directions. So we take another derivative, we get a minus v squared times cosine vt over r, and I left out an r. Right? And then in the y direction we get minus v squared over r times sine vt over r. All right, lots of equations. We're just going through and taking lots of derivatives. Okay? What that allows us to do, though, is actually calculate. So now we've solved for the x and the y components of the acceleration. I tried to tell you that the magnitude of the acceleration is constant. We have the components which certainly aren't constant. That's what I started with. But now we can solve for the magnitude. That's the goal here. So let's take a look. The magnitude of the acceleration is equal to the square root of ax squared plus ay squared in simple terms. Well, we could certainly do that. If we plug in our equations up here, we get something like, it's going to be a bit of a mess, minus v squared over r times cosine vt over r, and that whole thing is squared, plus minus v squared over r, not cosine, sine of vt over r, that whole thing is squared, and we bring the square root, a nice straight line. There we go. Okay, so we've got that big, long mess of an equation. We could do a little bit of simplifying here. We've got this v squared over r term that's going to be squared, so we can pull that out of the parenthesis, the first parenthesis, the inner parenthesis, I guess. So we get something like, and the negative sign, once we square that, that goes away. So we're going to get a v to the fourth over r squared. This should go all the way down. And then that's going to be times cosine squared vt over r. And the same term is over here, so I'll just pull that out in front and factor it, and I get a sine squared vt over r. All right. Now, if you're paying attention, you might see where this is going, because you know that cosine squared of anything plus sine squared of that same thing, that's equal to 1. All right, so this whole thing is just 1. And so what we're left with then for the acceleration is the square root of v squared, the square root of v to the fourth over r squared, which is just v squared over r. All right, if you've taken physics before, that might look familiar. This is called the centripetal acceleration. Centripetal acceleration. And that's where it comes from. All right, just a little bit of trig and a circle. All right, centripetal acceleration, what that really means, and we usually subscript this A with a C to stand for centripetal acceleration. That's the acceleration that an object feels that is going in a circle. All right, in order for the object to go in a circle, it must be accelerating. Remember, like from a week and a half ago, we said if anything's going in a straight line at a constant speed, no acceleration. If something's going at a constant speed and it decides to turn, it has to accelerate in order to turn. All right, it accelerates in what direction? Towards the center. So if we go way back up to this picture up here, the acceleration vector at all of these points is like yay. And we label that centripetal, A sub C. All right, so the centripetal acceleration is always perpendicular to the velocity vector. All right, the centripetal acceleration is always perpendicular to the velocity vector. It's always perpendicular to the velocity vector and always has this constant value, v squared over r. Nice easy equation, which is great. We like easy equations.